Hello and welcome everyone, and in this video we will be discussing about the design philosophy behind the tension members. So if we look at the tension members, there are two reasons. One is at the joint and one is without the joint. And at the joint there are holes in the member. Okay. And the remaining length is without hole. So there are two regions in a tension member. One is the tension member without holes or beyond the joint, means that portion which has no holes at all, and that which is beyond the joint. Whereas the other portion is the tension member with holes. So that region which is within the joint region. Okay. So these two regions have two different phenomena of failures. And if we understand the failures in the tension joints, then only we can analyze those failures and can derive to some useful formulas for the design strength of tension members. So what happens in the region of tension members without holes? Means there are no holes in the tension members. So when we apply tensile load on a tension members, and if we go on increasing the magnitude of the tensile load, as we have seen in the stress strain diagram, that the yielding of material start occurring. Okay. And yielding is like a plateau phenomena where the strain constantly increases without increase in the stress. So even if we do not increase the load, what is happening? The member is elongating and elongating and elongating. And what happens due to strain hardening? Although the strength increases for time being, but the structure will fail as soon as the load will reach the fracture point. So more elongation before the fracture due to yielding makes the member or the structure unserviceable. How many of you would like to live in a room in which the overhead beams of the ceiling are too much bending? No one would like to go inside that room. Everyone will be fearful, isn't it? So such a structure become unserviceable. Alright. So the first failure in tension members is the yielding of the section. And which type of section? Gross section, because there are no holes. Okay. And the second type of failure occurs in the tension members with holes. So when we go on increasing the load, there may be net area failure or there can be block shear failure. So there are two kinds of failures of tension member associated with the increase in excessive load. And this happens near to the joint, okay, where there are holes provided. Now net area failure and block shear failure is something we will discuss very soon. So if we conclude all these failures, we can write the design strength of a tension member will be minimum of the following. So there are three kinds of failures that happens in a tension member, and these failures decide the three strength values for the design strength of tension members, and we choose the minimum value out of all these three values of a strength, and the minimum value of a strength decides the design strength of tension members. So the very first type of failure is called gross section yielding, or in simple word, there is yielding at the gross sectional area. So in this case, more displacement before the fracture failure. Okay, this we have just now discussed in this case. And the second type of failure is net section failure. In net section failure, there is failure at net cross section. Okay, and we have discussed how the failure occurs at net section area, and if there are holes like this, so this kind of failure is called the net section failure. Okay. Then the third type of failure is called the block shear failure. Now, block shear failure is a combination of tension failure and shear failure, in which a block of the member got separated. So it is written that a segment of block of material at end of member shears out in a smaller joints. So what happen if we have a joint like this, and we have provided few holes here, and there are two rows of holes like this. So what happen if we go on increasing the load here T? So what happens, there is shear failure across these bolts and tensile failure across these two bolts, and consequently this block is separated out. So such a failure is block shear failure. All right. So the next point says there are two limit states to be considered. Limit state of yielding in gross section, and this is done to avoid excessive deformation in member. Okay, to control excessive deformation, so that the stresses in gross section remains less than Fy. So the first type of limit state, and in this case gamma mo is equal to 1.1. Okay, and there is limit state of fracture in the net section to avoid fracture in net section, so that the stresses in net section remains less than the tensile strength, and in this case gamma ml is equal to 1.25. And limit state of block shear is a combined shear and tension failure. So we will be discussing all these three types of failure in detail in this video. So if I talk from the IS 800 2007, so if you open the section 6, so the section 6 is all about the design of tension members. Okay, and you can read all these theory from the IS code itself, that tension members are linear members in which axial force act to cause elongation, stretchage. Okay, and such members can sustain loads up to ultimate load, at which they may fail at rupture at a critical section. So this critical section or the net section becomes very critical, and failure occurs there. That's why the calculation of net sectional area is very important in case of tension members. And however, if the gross area of the member yields, so gross area is the AG, and AG may yield over a major portion of its length, because there is a portion which is without holes, and if we increase the load, so that length may also yield. So yielding of that portion is also considered the failure of the joint, and the member may become non-functional due to excessive elongation. So the third kind of failure is also written here, that the plates and other rolled section in tension may also fail by block shear of end bolted regions. So all the three failures are summarized in this paragraph 6.1. Okay, so this IS code you can always read. This is very informative for us, and we must go through this section 6 if we want to understand design of tension member. And design of tension member is not very difficult. It is the most easiest part of the steel design, because there is only three formula that we have to understand apart from calculation of net sectional area. So here it is said that TD is the design strength of the member, and we have to calculate this only in all the numerical problems. What is the TD of the tension members? So it is written in the code that design strength of a member under axial tension TD is the lowest of three values. So the first value is the design strength due to yielding of gross section, and that is represented by TDG. Second one is the rupture strength of critical section, which is represented by TDN. And block shear TdB given in section 6.2, 6.3 and 6.4, which we will discuss respectively. So the value of TD will be the minimum of all these three strength value. So now our goal is to calculate TDG, TDN and TDB, which is given in section 6.2, 6.3 and 6.4. So first of all, let us calculate the design strength due to yielding of cross section, and this is very easy to understand. This is called TDG. Okay, and it is governed by yielding of cross section. So here cross section is under consideration, that section which is without holes, that section which is beyond the joint. So in that case we have to calculate first of all AG. AG is what? AG is gross sectional area, and this is equal to width of the member into thickness of the member. So this is very easy to calculate and we can do it within a moment. Next, we have to multiply this gross area with the yield strength of the material, and normally yield stress Fy is equal to 250 Newton per mm square, isn't it? And then we have to divide it with the partial safety factor gamma MO. You see this gamma MO, and this is equal to 1.1 in case of failure in tension by yielding. So this is very easy to calculate TDG, and the calculation of gross area is not very difficult. Now comes the 6.3 section, which is very important, because here we have to use net sectional area, and this is the design strength due to rupture of critical section. So critical section is where? At the joint, and at the joint there are holes, and those sections are called the critical sections, and at the critical section plate ruptures. Okay, so there are two kinds of the member made of. Member can be made of either the plates which have a squared edges or the rolled section like angles. So first of all I am talking of the plates. In case of plates, what happen? So the design strength in tension of a plate TDN as governed by rupture of net cross sectional area AN. So here we have to calculate the net sectional area AN at the holes is given by this formula. Now this formula is almost similar to TDG, but here we are also multiplying a factor 0.9, and this is multiplied by net area into FU. FU here is the ultimate stress of the material, not the yield stress. Okay, this is ultimate stress of the material, which is equal to 415 Newton per mm square for Fe 415. All right, and AN is the net effective area of the member. So calculation of net sectional area is very important, and then be divided with the partial safety factor gamma ml for failure at ultimate stress, and gamma ml is equal to 1.25. all right, so all these things we have discussed already, and the calculation of net sectional area in case of plates has also been discussed, that AN is equal to B minus NDH plus summation of pitches square by 4 times gauges, and this whole in bracket is multiplied by the thickness. Now B here and T here represents the width and the thickness of the plate respectively. Now what is this DH? DH is the diameter of bolt hole, and this is equal to 2 mm in addition to the diameter of the hole. So everything is written in the code, and we can just have a clear reading of all the information that is given, and we can take the help of all the formula which is written provided already, and we need not to remember these. Okay, so you can directly see these formula from the IS code itself. Okay, now DH is equal to D plus 2. Okay. G is the gauge length between the bolt holes. Okay. And if there is uniform gauge and uniform pitch, then we just multiply it or write it as M into P square by 4G, when the pitch is P and G is the gauge in the uniform situation. And M is the number of a staggering. Okay, M is the number of a staggering of the cracks at the critical section. Now if there are non-uniform pitches and non-uniform gauges, then we have to do the individual summations of all the staggerings and of the crack or the critical section under consideration. So G is here the gauge length between the bolt holes, and PS is the staggered pitch length between the line of bolt holes. So you can see what is this PS representing here. This is the pitches between the staggered bolts. And what is this gauge? Gauge is also represented here. And DH is the diameter of hole, B is the width of plate. N is the number of bolt holes in the critical section. Just like in this figure, if I talk, the value of N is equal to 5, isn't it? There are 5 holes in this critical section, and I is usually used in the summation for as a matter of subscript for summation of all the inclined staggerings or the legs. Okay. In chain pattern, the calculation of net area is what? AN is equal to B minus N times diameter of hole, and you multiply it with thickness in case of chain pattern of bolting. So that's not very difficult. But in case of rolled section, the calculation of net sectional area is little different. So first of all, I will talk of the single angles. Now what do I mean by single angles? That means that there is a built up section, just like you see this is a built up section. Okay, and here one single angle is connected with the plate or the gusset plate. So there can be single angle and there can be double angle. And what happens in case of single angle, one leg is attached, and in double angle there are chances that 2 legs are attached. And we have discussed how do we analyze the double angles in which the 2 legs are attached. We simply turn the angle like a flat plate and do all the analysis. So first of all, let us discuss about the single angles, that what is the formula of TDN in case of single angles. So at single angles, the formula changes a slight bit, and the rupture strength of an angle connected through one leg is affected by shear lag, and the design strength TDN is governed by this formula. And TDN here is slightly big, but it's not very difficult to calculate. Okay, TDN is same as 0.9 ANC into FU by gamma ml. Okay, now there is slight addition plus beta AGO F by gamma MO. Okay, where beta is equal to 1.4 minus 0.076 WYT into F by FU into BS by LC, and it should be less than FU gamma MO divided by FY gamma ML, and it should be greater than 0.7 also. So all the notations are also given here. What is W, what is BS? So to understand W and BS, you have to see this figure. If there is a single angle in which a single leg is connected with the gusset plate, and this is the diagram in bolted condition. Okay, and this is the diagram of single angle connected in tension member with the gusset plate in case of welded connection. Okay, you see the belts here being done the darker triangles, and this is the bolt here. So in case of bolted connection, the value of Bs is given by this formula. Now you have to look at this formula which is given here, Bs. What is this Bs? Bs is called shear leg width. Okay, you see this, Bs is called shear leg width, and W is called outstand leg width. So these leg width you can see in case of bolted connection single angle sections, W is the outstanding leg width. Now there are two legs in case of angles. One leg is the outstanding leg and other leg is the connected leg. Okay, in case of angle section, one leg will be outstanding leg or the hanging leg like a cantilever, and other leg will be connected leg. So W is the outstanding leg width. Okay, and Bs is the shear leg width, which is equal to W plus WL. Now WL is this, the distance between the bolts to the root of the angle section. This is the root of the angle section minus thickness of the angle section. Okay, so this calculation of Bs shear leg width is very important in case of bolted connection of the single angles, because most of the time you encounter bolted connection only, whereas in case of welded connections the W value will remain same for the outstanding leg width, but the shear leg width Bs here will be equal to the W or the outstanding leg width. Okay, so this is the difference in welded and bolted connection in single angles. So after understanding Bs and W, next is the LC, and LC represents length of the end connection. So we have to take the entire length of the end connections. So the length of end connection is the distance between the outermost bolt in the end joint measured along the load direction, or the length of weld along the load direction. Okay, so it is the entire distance between the outermost bolts. Okay, if I have made the joint like this, okay, and this is connected with a plate like this, and there are almost 5 bolts. So I have to take the distance between two outermost bolts, and this will be represented as length of end connection. So now you understand the distance between the outermost bolts is the LC, or the length of the end connection. Okay, T is the thickness of leg. This will be given for the angle section. Now how to calculate the gross area of the outstanding leg only, because there are two legs here. One is the outstanding leg, this one, and other is the connected leg. So AGO here is equal to gross area of outstanding leg only. Now AGO will be equal to W minus T by 2. This T by 2, why it is done, I will tell you. W minus T by 2 into thickness of the plate. So this is the gross area of the outstanding leg, because outstanding leg has got a width equal to W, but here we are subtracting minus T by 2. Why? Because there is rounding in the angle section at the corner. You see, at the toes there is rounding, and due to rounding we subtract minus T by 2 also. Alright, so that's why we subtract here from the outstanding leg width and then multiplied with the thickness. Next is the ANC. Now what is this ANC? Why it is called ANC? Because the connected leg has got bolting done. So there are holes in the connected leg. So we will not calculate the gross area of the connected leg. We will calculate the net area of the connected leg. Now how to calculate the net area of connected leg, ANC? So ANC will be equal to, now if the angle section is equal angle section, so if the width of connected leg is also W, then I have to subtract minus t by 2, as it is a rolled section having a rounded edge at the toe, and I am going to calculate net area here of the connected leg. So I will also subtract the number of diameter holes, okay, NDH, okay, and then multiplied with the thickness of the plate. So this is how ANC is calculated. And net area of the total cross section will be sum of net area of connected leg and gross area of outstanding leg, okay. So all these values will be used in this formula. Now let us come to the first of all beta. So you know the value of W. W is the outstanding leg width, T is the thickness of the angle section, Fy is the yield stress, Fu is the ultimate stress, Bs is the shear leg width, okay, and LC is the length at end connections, okay. So all these values are available and we can use it and get the value of beta. Now after getting the value of beta, we can use it in the equation of TDN and we can calculate the value of rupture at the net section TDN, and TDN is equal to 0.9 into ANC. Now ANC is the net area of the connected leg which we have just now discussed, and Fu is the ultimate stress. Gamma ml here is equal to 1.25 as usual, and beta we have just now calculated. AGO is the gross area of outstanding leg, and Fy is the yield stress, and gamma mo is equal to 1.1 as usual, okay. So this is very easy to understand. Now what is happening here, actually this formula is combining both the effects in the angles. It is combining the rupture at the net sectional area of the connected leg, and it is also considering the yielding of the gross sectional area of outstanding leg. You understand this formula? Here TDN is a combination of two things. One is the net sectional area of failure of the connected leg, and formula is looking similar like in the case of the plates, and this is the gross sectional yielding of the outstanding leg. So there are two legs in the angle section, one is the connected leg and other is the outstanding leg, and we are considering that connected leg is rupturing, okay, at net section, and the outstanding leg is yielding. So this formula is a combination of two, and here we have used a factor beta and outstanding leg width and shear lag width and the length of end connections. These things are easy to calculate, and if we do this we can easily calculate TDN also in case of single angles. And we have discussed about the double angles also, and how to analyze that we will learn it in the numerical sections also. Now let us come to the section 6.4, and here we will discuss the design strength due to block shear. Now the strength as governed by block shear at the end connection of plates and angles is calculated as below. So TDB, the block shear strength of connection, shall be taken as the smaller of two values. So the first value is this and second value is this. So we have to calculate both of these values of TDB, okay, and the minimum of these two values will be considered the final value for TDB, okay. Now the first formula says TDB is equal to AVG into Fy by root 3 gamma mo plus 0.9 into Atn into Fu by gamma ml. And similar to the first formula, second formula is a reverse, and it is equal to 0.9 avn Fu by root 3 gamma ml plus Atg F by gamma mo. So here are 4 areas that we have to calculate. Okay, and we know most of the notations here. Fy is the yield stress, and gamma mo is equal to, as usual, 1.1, and Fu is the ultimate stress, and here gamma ml is equal to 1.25. So if you look at any formula in the steel course, gamma mo is always associated with Fy, isn't it? And gamma ml is always associated with Fu. So yield stress is associated with partial safety factor 1.1, and ultimate stress is associated with higher partial safety factor 1.25. So this is very simple clue that you can remember in case of different partial safety factor values. So now there are 4 areas here that is also discussed, and we have to calculate first of all AVG and ATN and AVN and ATG. So these 4 areas are also written in the next phase. Now AVG and AVN is the minimum gross and net area in shear along bolt line parallel to external force respectively. Okay, so V here represents for the shear and T here represents for the tension. See, there is a combination of failure in block shear failure. One is the shear failure, so we consider those phases as shear phase, and there is failure due to tension also, and that is on the tension phase. So this is a figure of block shear failure, and this is in case of a plate 7A, and 7B here represents the block shear failure in angle section. Okay, so you can see in case of plates how this block has got separated. Okay, and in case of angle also how this much block has got separated. And in this case, if we see at this phase which is parallel to external force, now this is external force, and shear is parallel to the external faces, just like in figure 7a it is the 1 2 and 3 4. These two faces are subjected to shear forces. Okay, so here the sign of forces is also represented as like this, whereas in the case of angles you see this 1 2 section, this is only subjected to shear forces here. No, the direction of shear will be opposite to the external loads, but it will be parallel to the external force. So the same thing is written here, that 1 2 and 3 4 as shown in figure 7a and 1 2 as shown in figure 7b. All right, so these faces are being sheared out in the block shear failure. Now what is ATG and ATN? So ATG and ATN is the minimum gross and net area in tension phases perpendicular to the line of force. So here the phases is 2 3 in case of plate, and you can apply the tensile forces here like this. And if we calculate the gross area and net area of phase 2 3, that is equal to ATG and ATN. Similarly in figure 7b, 2 3 phase will be subjected to tensile failure. So we have to calculate net and gross sectional area of this much section 2 to 3 in case of figure 7b. So we will be discussing this block shear failure separately in numerical sections in detail, and do not worry about that. So this is how we calculate the value TDG, TDN and TDB. So after calculating all these three value of tensile strengths, we take minimum value of all these three, and that value becomes the design strength for the tension members. So this is all about the design philosophy behind the tension members, and we will be discussing few more numericals. So this is all about the design philosophy behind the tension members, and we will be discussing almost 3 to 4 numericals in the upcoming videos also. So till that, stay tuned and stay safe. Thank you.